Swayam Prabha. Digital India. Educated India.
Welcome to the class of intelligent product design. Now, we are going to talk about the high precision actuators today. So, these are, as you have seen earlier, that electrohydraulic and electromagnetic actuators, they are good, they have high power, but A is that their response time is slow, and B is that they are not so precise. So, for very precise movement, something like you have these for example, this SLR camera, I always give this example. The camera is today's camera is one of the example of a intelligent product which is very high precision. Now, such a thing in a lightweight situation, you cannot actually have electrohydraulic or electromagnetic system to drive them, but you need a piezoelectric system to drive them. So, these are some of the situations where you need basically high precision actuators. Now, we will talk about high bandwidth, low strain actuators now, and particularly the one keeping this type of applications like these advanced camera optical systems, etc. We will focus on multi-layered piezoelectric materials, okay? And we will show that in this case how you have to do the mechanical model and the electrical model together. We can also use it for another type of application, which is for the application of such a system for grippers. So, we will show it here, and we will also show some of the advantages of such actuators and how you can develop them. So, common smart actuators that you might have seen is like the disc buzzer, okay? The one that is there in a bike, for example. So, where you have a metal disc which is attached with a piezoelectric material, and then you can vibrate the piezoelectric material, which will vibrate this disc, and that will create this sound that these bikes and typically this type of horns actually make. Now, another application is for an amplified piezoactuator system. So, amplified piezoactuator system, basically what it does is that the stack is here inside, and because the force is high, but the deflection is low. So, it takes into account this kind of a mechanism. Okay. So, which what happens is, if large force here, because the stiffness is very high, will create a large change in the deflection in these directions. Okay. So, that is how the deflection or the stroke is taken from a 90-degree kind of an angle, so that you get maximum displacement out of the system. This is something that is heavily used amplified piezoactuators, and again the DSL are cameras, that single lens reflectors of digital camera, that will be using these piezoelectric stack actuators and the Epson printers. All of them are very good examples of these piezoelectric actuators. Now, another part in which piezoelectric actuators are used is this automotive electronics. One of the best example of it is the piezo fuel actuator, and then piezoelectric pressure sensors and piezo level sensors, etc. So, this is one way the stacks work in an axial direction, but if you want to produce some kind of bending, etc., then you have to use unimorph, bimorphs and all these things, but they are not so popular because of reasons of efficiency, lower displacement and safety, etc. So, mostly the piezoelectric actuators and rheological fluids in a stack mode are used for this fuel injection and motion control in automotives. I will show you one particular example of this fuel injector, piezoelectric fuel injector, like the Bosch piezoelectric fuel injector you can see here there are so many piezoelectric stacks stacked one after the other, right. I am just showing you very broadly. So, now what happens if you apply a voltage, you will get a large force generated, and this large force will control a switch valve, and that switch valve, once it is open, then the fuel will be injected into the system. And because of the very high bandwidth, that means very fast response time you will get to inject the fuel at the proper moment. Now, if you compare the performances of conventional system versus such system, you would see why it is high precision. See these actuators, it has a precision of 0.01 micron meter. Compare it with electromagnetic system 10 micron meter. So, you can see that it is something which is much more 3 orders of magnitude more precise, and the response time is so fast, 4 orders of magnitude lower. Okay. So, it is very fast response time you are going to see in these systems, and that is of course piezoelectric. Magnetostrictives are little slower, and there are some ultrasonic systems which are also little bit slow. Now, this is the comparison of different actuators like the electromagnets and versus piezoelectric, and we can see how high precision is the piezoelectric actuators, and their response time is also very fast. What are the issues with PZT? Well, first of all, you need a very high electric voltage to develop a piezoelectric system. Okay. How high it is? Something like a 1 kilovolt field would be required. Now, if you remember the basic constitutive equation for generating this piezoelectric strain, let us say for example, the strain that you can generate is there are 2 ways of doing this, generating this strain. One is with the application of the stress itself. So, we know that stress is proportional to strain, sigma equals to E epsilon, that is there in all the materials, right. So, in fact, we can write it as epsilon here, that would be better for us, that the strain, let us denote it as epsilon. So, epsilon is 1 over E sigma, and that can be also written as S sigma, where S is, this is elastic modulus, this is elastic modulus, E is elastic modulus, this is E, and S is, we will say it as compliance modulus. Okay. So, that means I can write epsilon equals to S sigma, that is a normal Hookean relationship, but then in addition to that, for a piezoelectric material there is this electromagnetic coupling coefficient D times E, that is the electric field intensity, that can also generate the strain, that is the active strain. Now, we are going to focus on this part of the strain. Okay. So, now what is the electric field intensity? E is the electric field intensity. Now, this electric field intensity can be expressed as applied voltage over the thickness. So, that means if I have a piezoelectric block here, and if I apply a voltage V, then if the thickness is T, then the electric field intensity is V by T. So, that actually tells us that if somehow I can reduce the thickness very small, bring it down, then the electric field will actually go up. That is the technique that we adopt for a piezoelectric block or stack actuator. We take many thin slices, so that we get a high electric field, and through high electric field we can generate a high active strain in the system. How we do it? Let us look into it. So, here you have many piezoelectric systems, okay, and you can see that they are stacked in a manner that each one of them are stacked together, either possible to have in a series or possible to have in parallel circuit. Okay. and mechanically if you think of each one of them to be something like a spring, then in this arrangement they are all these springs are in parallel to each other. So, are in series to each other. So, this is a typical series in terms of the mechanical system. Electrical system, however, it depends on your plan of connectivity. You can make it parallel or you can make it series. Now, under this kind of a system, what is the complete deflection that you are going to get? Well, of course, you have each one of them you are applying the same voltage. Okay. So, something that you are doing when you are connecting this entire system together and you are applying each one of these discs with the voltage V, and then the total length is L, and if there are n such discs, so the thickness is L by n. So, this will give you a high electric field E, okay, multiply it by D, electromechanical coupling coefficient, then you are going to get the strain, and strain times the original length L, this is actually the original length L, you are going to get the complete deflection in the system. And you will see that this is dVn, which means the larger this number of discs with the same voltage, you can get much more displacement, because it is simply a function of the layer number n. Now, typically the layer thickness is about 50 micron meter and a typical strain available is 0.1%. So, for a 100 millimeter stack actuator with 2000 piezoelectric layers, the applied voltage about 100 volt, the displacement you will be getting is about 200 micron meter. And if you try to stop it, you are going to get a 100 kg force, and the lifetime will be 10 to the power 11 cycles. So, that shows that how much robust and how much large force you can generate from a small compact actuator system. Now, this can be used, this powerful system can be used to actually create the grasping of a robot. That means, a robotic end effector, we can use this system. So, the stack actuators can be used in this kind of a system, which you can call to be robotic end effector. So, this is an end effector. End effectors are always the last part of a manipulator that is used in terms of picking up certain loads. Okay. Now, this end effector, how it is working? So, the force is coming here, okay, as has been shown here, so at this position, and in order to operate that means it can go this way or that way. So, this rotation you have to do. Now, if you have to do this rotation, accordingly you have to move this point with respect to this position, the point B, and accordingly you need to move this point A, and this point A movement is controlled back and forth. Okay. So, that means, if the point A comes here, then accordingly the point B goes there, then accordingly the point C, and then accordingly the grasper releases the force. So, something similar happens the other side also. Now, that means that you have to move this, and we try to move it with the help of a spring also. So, there is a spring and a piezoelectric actuator that works together. Now, two relationships that is important here. One is the electric field displacement charge part of it, so that the stress will generate the charge in the system. Another important thing is what is the strain, and there the electric field is generating the strain. The negative sign I have given here, because that corresponds to basically tension positive. So, that you can create a compression or tension in the system. It is just a matter of sign convention. And each one of these piezoelectric system, if you look at it, piezoelectric material is having electrode coating in top and bottom, and that electrode coating is actually applying the voltage, so that the deformation is happening in the system. Now, then you can actually get this total length change with the help of the mechanical length change and the active length change, that is the active part of it, and similarly you can get the voltage generated in the system. So, if you further work on it, that what is the force that can be delivered by the piezo stack to the gripper, then you know that it is working against a spring, because you know that there is a stack here, and then there is a spring that moves these 2 points, that point A, if you remember, and that moves the grasping system. So, the force that is going to come up is actually K times the the stiffness of the spring K. So, K, and then the difference between this movement here and the movement at this point, that means the relative displacement between the two, that is what is going to give us the force that this is going to apply into the grasper. So, it is K con Z minus delta LST, and where this delta LST is actually coming because of that piezoelectric material. Now, delta LST then from this relationship can also be written as Z minus FST by K con, and this K con connectivity of the stiffness system, it can be considered like an axial beam which has a cross section A and length L and modulus of elasticity E. So, that the K can be written as AE over L. So, we know the stiffness, and because we know the stiffness, okay, we can either if we know delta LST, we know the force, or the other way round, we can use the system. Now, there are many possibilities, as I told you, that if mechanically the system is in series and also electrically in series. Electrically in series means all of these piezoelectric materials are connected together. Okay. So, electrically in series system, and mechanically in series, I told you that each one of the disc are modeled like this. So, this is a series solution, and mechanically when it will be parallel, that means the discs are kept in this mode. Okay. So, this is how the force is applied to the system, and electrically parallel is something like this, that you are having main line, and then you are having this connector here, and you are having this connector here. So, every alternate one you are having this and the connector here with this system. So, like that it will be electrically parallel. So, for this system series, VST is N times the voltage, that is the total applied external voltage in the system, that is N times the voltage. N is the number of layers that is there, and V is the voltage in these each one of these points. And what is the force here? FST. FST is the total force that is coming, because that is the force is passing through the entire system, and we can write it in a way that delta LST is actually N times the delta L. So, that is the deflection of each element is delta L, and if there are N such systems, then the total deflection is N times delta L. Now, with that we can write down the equation again, that total deflection delta ST is 1 over EP, that is the compliance modulus I told you, FST over A, that is the applied stress, and then N times L because it is in series, and then minus D33 VST. So, from this you can calculate what will be the stack force. The same thing you can do for mechanically parallel and electrical series system. Electrically series, so VST is NV, and mechanically parallel, so FST is N times the force now, and hence you will now get a modified relationship for the system. Now, similarly, if you go for mechanically series and electrically parallel system, so in this case now FST will be F only and VST will be V only, and hence the relationship changes accordingly. So, you can thus get all these different combinations, be mechanically parallel, electrically parallel, FST will be NF and VST will be V, and hence you get the relationship between delta LST and VST. So, all these things that you can get, like all these different combinations of the system, you can actually put all these things together in a diagram, where you can show that if it is a series connectivity, you get these force voltage relationship. Ultimately, I am interested in the force and voltage. Applying how much of voltage, I am getting how much of force, so that I can move these grasping system to a certain distance. I can open it up or close it. So, series will have some relationship, series parallel will have another relationship, parallel series and parallel. You will get 4 such grasping relationship that is possible in the system. Now, PZT actuators, I have just shown you one example of it, but then there are many other examples of such a system. For example, if you want a high mechanical compliance of the stacks, then we go for P601, 602, 603, etc. If you want to get a high mechanical stiffness, then you use the P882 or P888 type of piezoelectric material. If the response time low is okay, you take this, you can use this 885.55, and if the high robustness to electrical disturbance is required, then you take this particular grade of a piezoelectric material. So, thus you have a broad choice of such piezoelectric materials for different applications. Now, what are the governing criteria? PZT actuators showing higher mechanical compliance should be modeled as a series, because we know that in series the stiffness is reciprocal in its relationship, right. So, if you have 2 springs here like this, K1 and K2, then the equivalent stiffness K equivalent is 1 over K1 plus 1 over K2. In other words, K equivalent will be K1 K2 by K1 plus K2. So, this is certainly lower in comparison to if you take 2 springs in parallel, K1 and K2, then K equivalent is K1 plus K2. So, that way you are getting a larger stiffness. So, if you need a higher mechanical compliance, then you can model it in series. In the electrical domain, PZT actuators having faster response time should be always modeled with a series assembly, okay, of these are basically capacitors, okay, and those showing higher robustness to electrical disturbances, they need to have a parallel circuit. So, depending on the applications, we need to choose the circuits and the stack arrangement. Another important factor here is the resonating frequency of the actuator, because every actuator, if you can actuate it at the natural frequency of the disc, then that is the resonating frequency. So, that resonating frequency is one important constraint, that if you go up to that point, there may be a situation where the disc can break. So, if a sample is having say 100 kilohertz of resonating frequency, then you need to operate lower than that for a grasper kind of application. Now, what are the advantages of such multi-layered piezoelectric actuators? They are very versatile and intelligent actuator for us. Well, one is that of course, they require less voltage, because they are stacked, as I told you. They can produce large deformation. This is also because of the fact that the electromechanical connectivity D33 in this case is much greater than D31. They are safer to use because low voltage, high life cycle, lighter and more compact, and you can do concurrent engineering from such capacitors. You can design it as you are designing the manipulator or such actuators. Now, how do we then develop such a system? There are 2 techniques. One is called a cut and bond technique, another is called a tape casting technique. So, cut and bond technique, the PZT wafers are cut typically of thickness 0.2 millimeter and bond with intermittent metal foils. So, major drawback is that this is a labor intensive process, because you need to chop it very thin, and piezoelectric materials are very brittle. So, cutting them is not so easy. Tape casting technique on the other hand is where you prepare a ceramic green sheet, and then on that green sheet you apply electrode and then co-fire the system. So, such a system, this is the process by which you can develop such a system, that the tape casting, you take a powder, mix it with some binder, prepare a slurry, then slip cast it on the system, that slurry, prepare a green sheet and then apply the electrode over it and then laminate it, high temperature pressure, then cut it and fire it. After once the firing is done, then of course you have to electrode it and then the device is ready. That way cutting and bonding process is much faster. You sinter the bulk, cut it into very thin part, polish it so that all loose materials are over, then electrode it, bond it and stack the device. So, that way it is faster. Now, these multi-layers can be actually developed in the form of not only the stacks, but also in terms of a sandwiched inside a substructure, two substructure, inside you have the actuator. So, this actuator is actually when it contracts, then the two sides you are getting one side expansion and another side contraction, and which means you can create a bending in the system. Now, if you want to create a bending, so you can actually see that you have the force total, you can equally have an equilibrium between the tensile force and the compressive forces. So, FB1 is FA plus FB2, depending on that FA you can always change the nature of the force, and the moments you can sum up all the moments together, and then you get the two relationships, the governing relationships of the system. That actually gives the actuator governing equation, and the active force can be calculated first of all from the active strain, and then if you assume that there is a equal curvature of the composite system, then you can compare their EI over M. Well, once you have the governing equation of the system, then you can actually create a transfer function, because here we are controlling the bending. So, the transfer function is between the theta and the moment, and in this case you will get a second order transfer function in the system. And this transfer function I will later on show you, but right now I am in a control system design, but right now I am showing you that you can simply write it down as the plant. So, this becomes a second order plant, and you can create a kind of a a loop here, in which you are sensing the bending and then feeding it back and then controlling the current and have a closed loop system. So, thus you can have a closed loop actuator system in this particular case. Now, I will show you some applications of it. One is something which is very famous, it is called a Stewart platform system. So, this is used for active vibration control. Of course, in this case you are not bending the system, you are actually controlling for each of these legs their length, the leg length you are controlling. And remember, I told you that the stiffness of each leg is AE over L. That is the basic mechanical stiffness K of the system. Now, with the help of this piezoelectric material, if you can change this length L, increase this length L, then the stiffness comes down, and similarly if you decrease the length L, the stiffness will be more. So, thus you can vary the stiffness of each one of these legs by varying their length, and that you are doing by applying voltage to the piezoelectric material. What is the advantage of it? Well, the advantage is that this is particularly used for rockets. If there is a vibration that is coming from here, then by controlling the frequency, you can actually create a band gap. So, that those frequencies, suppose if it is very, very steep and this frequency is low, so it will not be able to transmit. So, the satellite that is sitting here, the satellite or the payload, they will be remain insulated from whatever is happening at this end of the system. So, that is a Stewart platform application. Another application where the piezo stacks are used is high precision micro positioning devices. This is a very common equipment in terms of different types of high precision manufacturing, and machining as well as for microscopes, confocal microscopes, etc. So, here they use a P545 Pi nano, and where the travel range is 200 micron meter, but you can do this change extremely fast because the bandwidth is very small, like within 5 millisecond, and the position you can control very good. You remember I told you that the position control is something like 0.01 millimeter. So, you can control it as 1/100th of a millimeter level, the positioning of the device with the help of controlling the piezo stack. So, these are the two applications of this concept for two intelligent products. Thank you.